Okay, I think I'm audible and visible, and let me just start the recording. So recording has been started. I will share my screen as well. So I hope the screen is visible and my voice is clear too. Okay, so let us just start the session. So good evening, everyone. Myself, Arka Roy. I'm working as a Prime Minister Research Fellow at Philippines. Okay. So, uh, good evening, everyone. Myself, Arka. I'm working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna. And I'm your NPTEL PMRF QA for this course on discrete time signal processing. This course is offered by Professor Mrityunjay Chakravarti, who is a professor in the Department of Electronics and Communication Engineering, IIT Kharagpur. So we have reached towards the end of this course. So this is the week 8 live session. So in week 8 live session, so this is the presentation layout. So we'll start by solving some questions, like we will be solving the quiz 7. Followed by that, we'll have a short recap of the content that is being covered in week 8. So in week 8, the main topic is basically the FFT algorithm, and there are several versions of FFT algorithm are there. So we'll be basically focusing on the DIT FFT, that is decimation in time, then fast Fourier transform, and which is of radix 2. So after that, we'll solve some sample questions related to week 8 that will help you in solving the week 8 course quiz. And later we'll have a short Q&A session where I will take some questions if you have any regarding the solution of the question. Okay. So let's start solving the week 7 quiz. In week 7 quiz, we had the FIR and IIR filter descriptions. And followed by that, we had also seen how to design the IIR filters, and we had also covered the bilinear transform. We are covering in week 8. So we have covered the impulse invariance method. So while in impulse invariance method, we had seen to design an IIR filter, we first need to design an uh, equivalent analog filter, or which we call an analog prototype filter. And then from that analog prototype filter, we have to map the analog Fourier transform to analog to digital Fourier transform. And then from there, we can find the impulse response and all. And additionally, we can get the Z transform of that particular filter. So let's just dive into the problems. So in week 7, the first problem is that, so this is a first order IIR filter, which has a transfer function of this HC is equals to Z to the power -1 minus A star. And the denominator is 1 minus AZ inverse. And it has been given that mod A is less than 1. So therefore, we need to comment about the filter characteristics. What is the magnitude characteristics and what is the angle characteristics or phase characteristics of this particular IIR filter. So let us start solving the question. So let me just change the color of the pen. Okay, so HZ is equals to Z to the power -1 A star divided by 1 minus A Z inverse. Oh, 1 second. Okay. So so it is given that Z transform is some sort of the Z transform is given like this. Now we need to change the variable. So Z, I can take it as e power j omega so that I can convert this to DTFT. So in place of Z, I will be writing e power j omega. Therefore, it will be h e power j omega is equals to e power minus j omega minus a star or conjugate of a, and then I can write it as a 1 minus a e to the power minus j omega. Okay, so I can even write it like this: h e power j omega is equals to e power minus j omega. I can take this e power j omega out from this numerator and I can write it like 1 minus a star e power j omega. And then I can write the denominator as it is. So this thing I can also rewrite as, so denominator will be as it is a power minus j omega. And here I can see that 1 minus a e power j omega, and then I can write it as minus j omega, then I can write it as star. So in last class also I had discussed a property. If z plus minus z star is written over here, so I can write it as z1 star plus minus z2 star. So from this logic, what I can do over here is that I can write it as 1 minus a e power minus j omega. So I am taking star. So if I take star of it, so e to the power star will come and e to the power minus j omega, it will be converted to e to the power j omega. And 1, as because it's just a real term, so 1 star and 1, they will be alike. So therefore, I can see that I'm getting some sort of representation which has been replicated over here. So I can conversely write it to this particular form. So that is what I have done in this particular line. So given this, I can rewrite it as e to the power minus j omega multiplied with 1 minus a e to the power minus j omega star divided by 1 minus a e to the power minus j omega. Okay. So now we can take the modulus of h e power j omega to get the magnitude spectrum. So therefore, let me just take the magnitude of this particular representation. So, so I can just copy this part from here. So over here, I can just copy this thing and I can write it as h e power j omega. So if I take mod of this, so mod of this will be mod of this whole thing. So now from another property, we know that if Z1 and Z2, these are multiplied and then I have, if I take the mod, so this will effectively mod Z1 multiplied with mod Z2. And additionally, there is another formula. So Z1 divided by Z2, and if I take mod of it, then I can write it as mod Z1 divided by mod Z2. So after that, if I just follow the relation, so it will be h e power j omega equals to e power minus j omega, and then I can write it as 1 minus a e power minus j omega, and then I can take this star over here and then 1 minus e power minus j omega. So then again star. So even eventually I can write it as h e power j omega is equals to, so e power minus j omega, if I take mod of this thing, so it will be effectively 1. So therefore I can write it as 1 multiplied with 1 minus a e power minus j omega divided by 1 minus a to the power minus j omega. And then I can take star over here. So effectively, if uh, mod z and mod z star, these two are same. So therefore, I can write it as 1 minus a e power minus j omega divided by 1 minus a e power minus j omega. So for that, I can see that mod of h e power j omega is equals to mod of h e power j omega is equals to 1. So I can see that it has become a constant value, constant value. So therefore, mm, the magnitude spectrum is having this particular relation that magnitude spectrum is a constant value. So option A and B are basically satisfying the h e power j omega is constant. So option C and D are already nullified. Now we need to talk about what is the characteristics of this particular thing, that is the phase of this filter response. So for that, if I have to calculate the phase response, so let me just write the governing equation of h e power j omega, that is e power minus j omega, then multiplied with 1 minus a star e power. So here it was a star e to the power j omega, and then 1 minus e to the power minus j omega. So conversely, sorry. uh, so conversely, we can actually just make some modifications, such as let a be r e power j theta. So we are considering that A is also a complex number, so which has this particular polar representation r e power j theta. So with this, if I just combine all the relations, so it will be e power minus j omega, then 1 minus r e power minus j theta e to the power j omega. And in the denominator, it will be 1 minus a e to the power minus j omega as it is. So I can write it as e to the power minus j omega multiplied with 1 minus r e to the power. If I just take minus j out, so it will be theta minus omega. Okay. And then over here, I can write it as 1 minus a e to the power minus j omega. So now let's just see some rules for calculating the argument or the phase relation. So if Z1 and Z2 are two complex variables with R1 e power j theta 1 and R2 e power j theta 2, so I can write it as R1 by R2 and e power j theta 1 plus theta 2. So therefore, for this Z1 by Z2, the angle, if I call it Z3, so angle Z3 is basically theta 1 plus theta 2. So this particular form we have to keep in mind, but this particular form should be in the polar representation, polar representation. So in complex number, there are two representations are present. So one is the polar representation and another is the uh, 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 so we call it basically the Cartesian representation. So where we can write it as A plus JB format, and if I just have to convert into polar form, so that will be magnitude A square plus B square multiplied with e to the power j tan inverse b by a. So this is what is basically R, and this is what is basically the theta part. So these are well known. So this is the angle part. So if I do Z3, Z1 by Z2, so the effective result will be R1 divided by R2 e to the power J theta 1 plus theta 2. So by this way, the angle representation will be like this. So here I can see, so there are two complex representation. One is 1 minus Rj power e theta, and another one is 1 minus A e power J theta. So over from here, I can get the angle representation. And another thing is that if I have sorry, so here I just have made a mistake. So it would be theta 1 minus theta 2, theta 1 minus theta 2. And another representation is Z1, Z3 is Z1 into Z2. So at that particular time, it will be R1 into R2 e to the power J theta 1 plus theta 2. So over there, the angle will be theta 1 plus theta 2, and over here, the angle will be theta 1 minus theta 2. So here I can see that one particular representation is multiplied with this whole thing. So therefore, I can use this particular relation where we are multiplying two complex variables. And over here in this particular region, I can see there are two complex number which are basically in relation with one Z1 by Z2 kind of thing. So therefore I can exploit this particular relation. So using this, let us just try to configure that what would be the phase relation. So from here, the phase relation will be minus omega, as because e to the power minus j theta. So e to the power minus j theta. So I can write it as e to the power j of minus theta. So this angle is basically minus theta. So here it is written as minus omega. So therefore, from this particular relation, I'm getting the angle is minus omega. Then there will be a plus sign, as because we already have seen that it would be plus, as because I will get some angle representation from this composite block, and which will be of, let us consider here, the total angle for this particular thing is theta 1, and for this particular part I will get theta 2. So it will be theta 1 minus theta 2. So we need to evaluate basically what is theta 1 and theta 2, and then we can see that whether the phase relation is linear or not. So for that, if I just copy it over here, so it would be h e power j omega is equals to e to the power minus j omega, followed by 1 minus r e to the power minus j theta minus omega divided by 1 minus r e to the power minus j omega. So let me, but still this part you can see, this part is basically the polar representation, and here also this part is polar representation. However, there is 1 minus terms are also there, which basically form some deviation from the previous relation that we have saw in the rule part. So here it was totally a polar representation, but here it is mixed. So we have some a real part over here, and this thing is basically a mixed polar form and Cartesian from these two are mixed. So what we can do is that we can expand this r e power j theta by the rule e to the power minus j omega, and then I can write it as 1 minus r cos of theta minus omega, and then it would be plus j sine theta minus omega. And over here, it would be 1 minus r cos of omega, and then plus j sine of omega. So if I just basically here I'm bothered about the angle part, so I will not be focusing on the whole calculation of this magnitude and the phase. So here I will have some a square plus b square, and here I will have some a naught square plus b naught square. But thing on which basically we are focusing on, that is the uh, phase relation. So the phase relation is basically what we are getting over here is from this particular part. The phase relation is tan inverse sine theta minus omega divided by 1 minus r cos theta minus omega. And over here, what we are getting is basically, so this is angle. So this is angle tan inverse. So I can write it as sine omega divided by 1 minus r cos omega. So from this particular area, we were getting the value minus omega. So I'm calculating the angle h power j omega currently. So here for this part is giving you minus omega. Followed by that, we will get a plus sign over here as because these two parts are multiplied. So if it is multiplied, then we have seen that it would be theta 1 plus theta 2. And by that logic, here is a plus sign. And however, here as because this is in the form of z1 by z2, so it will be theta 1 minus theta 2. So the angles will be negated with each other. So tan inverse of sine theta minus omega divided by 1 minus r cos theta minus omega. And then again, there will be a minus sign, which will comprise of tan inverse sine omega divided by 1 minus r cos omega. So in this particular relation, we can see that there is a minus omega component and there are some additive components and some other subtractive components are there. So if had it been only the minus omega part, so we could have said that this relation is a linear relation and which is quite needed in case of filtering. So we quite often require something which is of having finite length. However, as because it's an IIR filter, we cannot ensure finite length, but the phase relation that should be linear phase, that should be a linear phase. So in this case, had it been it was only omega, then we could have commented about okay, the phase relation is linear. However, these terms are basically introducing non-linearity with this particular minus omega. So we can say that the phase is not linear. And we had already got that the magnitude is constant. So therefore, the magnitude is constant and phase is not linear. So let us just check. So this is constant and He power j omega is not linear. So this will be option B. Okay, so let us move to the second question. So in the second question, it has been given that HC is a causal and stable IIR filter. If Z in HC is replaced by minus 2Z, then what will be the characteristics of the resulting filter? So whether it would be a stable filter or a causal filter, and if it would be non-stable or non-causal. So we need to check the regimes that what are the possible cases if I just replace Z by minus 2Z. So given that HZ is causal and stable. So I can write that HZ and stable IIR filter. So I can write that HZ is equals to summation n is equals to minus infinity to infinity. And let us consider the corresponding impulse response or the unit sample response if I be very specific about the discrete domain nomenclature. So it would be a unit sample response and then multiplied with z to the power minus n. Now, as because in the question they have already told that this is a causal filter. So for the negative part, there will be no component. So I can just consider from n equals to 0 to infinite, and then it would be same as it is that it's n z to the power minus n. Now the given argument is that we need to replace z by minus 2z. So let us do the same. So 0 to infinite h of n and it would be minus 2z to the power minus n. So I can write it as h of n minus 2 to the power n, and then I can write it as z to the power minus n. N is equals to 0 to infinity, that is h of minus 2z. So by definition, let us consider uh, Pz is equals to summation Pn z to the power minus n. N is equals to minus infinite to infinite, and let us consider Pn is also causal. So then n equals to 0 to infinite. So we can just compare from here. So here I can say that is a z transform of P of n. By that logic, I can say that if I replace this z by minus 2z, then the sample unit sample response is basically changed from h of n to hn multiplied with 2 to the minus 2 to the power n. So I can write it as the new unit sample response when z is replaced by minus 2z. So then it would be, let us consider it is h cap of n. So this is hn minus 2 to the power n, and as because we are actually working in the right hand side of the uh, samples, so we can say that there is a multiplication of u of n, as because un basically gives you the flavor of causality. So we have found that your hn is basically minus 2 to the power n hn multiplied with un. So when we are changing the argument, which was there z, now we have changed to minus 2z. Now the unit sample response is this one. And from here, readily we can say that as because un is multiplied over here, so then obviously the resulting signal or resulting filter response that will be causal. So this will be causal obviously as because we are multiplying a un over here. So option A and option B, these two are nullified. So we need to just check the second condition. So to check the second condition, so let's just do it in a graphical fashion. So let me just copy this part. So we have got this particular sequence, and let us consider a diagrammatic situation. So we'll choose a graphical method to solve this particular question. So the index variable is n, and we have un like this. So this is, we all know that is a unit, the amplitude is unity 1. And then uh, as because we'll be moving towards this side, as because we are multiplying with un, I will not bother about what is there in this particular region. And it is given that this is a stable filter. Original hz was a stable filter. So accordingly, hn will also be stable. So for a stable sequence, so let me consider a very generic stable sequence. So a stable sequence could be a decaying sequence. So could be like this. So when n reaches to sufficient large value, then it reaches to 0. So this could be a situation. And we are multiplying minus 2 to the power n with this particular sequence, and then whatever resultant. So this is hn, this is un, and then we can multiply minus 2 power n, then h and u1. So For stability, what we can do is that we can check the condition of stability. So it will be summation, and it will run from n is equals to 0 to infinity, as because we are actually bothered about the uh, right hand side sample. So n equals to 0 to infinity, then minus 2 to the power n hn, and as because un we are multiplying, that means for each and every sample we are multiplying one, so I'm not explicitly writing un over here. So I can break the summation like this. So it will be minus 2 to the power 0 multiplied with h of n. Okay. Then I can write it as minus 2 to the power 1, then h of n, and minus 2 to square h of n. So I can just rewrite these as corresponding index values also. So as because this is a stable, any decaying sequence are stable. So here also, if I just multiply some values with this minus 2 to the power n with this decaying sequence, so obviously the sequence again, it will also be a decaying sequence, as because at sufficiently large value of n, it is reaching to 0. So it will also, the multiplication thing will also retain the same particular formation. So as because this signal still, it becomes a decaying sequence even after multiplying with 2 to the power minus 2 to the power n, and it retains the decaying property. So therefore we can just talk about the stability is that the signal is stable one. And here also I can just show you some another so representation. So it will be so 2, then h of 1. And as because 2 is basically a number, so I can just write it out from the mod part. And again, it will be 4, then h2, and then it will go. But the thing is that as because it's a stable sequence, when n reaches to a sufficiently large value, it will be reaching to 0, or the values will become very less. So therefore, it will eventually, the summation will converge. And if the summation is converging, so this will be m, which is less than infinity. So therefore, the signal effectively be a stable signal. So therefore, the response, the IIR filter response, we have already seen this would be causal, and additionally we have also proved that the response will be stable as well. So we can say that this would be both stable and causal. Okay. So moving to the next question. So in the next question, we have given an analog filter, that is HAS, and which is a Laplace transform of s plus 1 divided by s plus 1 whole square plus 4. And it has been given that the real part of s is greater than of minus 1. And the digital filter corresponding to this is h of c, which is basically got from h of as, that is by impulse invariance method, that is basically covered in week 7. Assuming the sample period is t, we need to find out the z transform of the digital equivalent digital filter that we are trying to map using the impulse invariance method. So uh, to proceed, first what we have to do is that we need to find the equivalent time domain signal or time domain response of the unit impulse response of the analog filter. So for that, let me just write HAS is equals to s plus 1 divided by s plus 1 whole square, and then 4. So I can see some sort of pattern is coming. So it is 2 square. Okay. So if I exploit the properties of Laplace transform, so I can write that s divided by s square plus 2 square. So this is basically cos 2t multiplied with ut. So that is happening over here. So if I just omit 1, so it will be s divided by s square plus 2 square. Now, instead of getting this particular representation, we have been given this one. So what is extra that is happening over here? So in place of s, we are writing s plus 1. So that means there will be exponent of e to the power minus t and cos 2t ut. Okay, so this is difference. So cos 2t then ut. Okay. So I can say that HAT is equals to the power minus t cos 2t ut. Now they have been told that the sampling period is t. So I can write that h n is basically h of n t. So h a n t rather, because I'm sampling the analog signal with a time period of t, sampling period of t. So I can just first write HA and T is equals to e to the power minus NT. In place of small t, I'm just putting n multiplied with capital T. Then cos 2 into NT and then U into. So effectively, I can write the digital equivalent signal as e to the power minus t to the power n, then cos 2n multiplied with u. No, sorry. So UTN and then UNT. So UNT, UT, you can just conversely write. So you can write it as UN as well. So this is the equivalent digital domain or discrete domain. Discrete domain filter unit sample response. But what we need is that we need to find this h of z. That means we have to take z transform of this thing. So we have to find the z transform of h of n so that we can get hz. So that is basically our main aim for this particular question. So if I now write h n is equals to e to the power minus t to the power n cos 2t n. So let us first see some of the properties of Z transform. So properties of Z transform. So first property would be a to the power n multiplied with un. It would be having the Z transform as 1 divided by 1 Z inverse. And I can write it as AZ inverse is less than 1. And therefore I can write the mod Z is mod Z is greater than mu. So these things we know. So I can conversely write it as in this fashion also Z divided by Z minus A, and the ROC is defined like this. So this is a to the power n q. And additionally, this is property 1. The property 1 can also be exploited in this particular fashion. So a to the power n xn. So let xn has z transform x z, then a to the power xn. So this is a scaling property. So a to the power xn will have x of z by a. So if we just exploit this xn as un, so you can just put it like this. So for un, it is 1 divided by z inverse. So if I multiply a to the power n un, so this will be 1 minus. In place of z, it would be so I can write it as 1 divided by 1 by z. So in place of z, it will be z by a. So it will be z by a. So I can write it as a by z. So therefore, z divided by z minus a. So which is written over here. So this is just for illustration part of this second rule. So we'll be exploiting these particular rules to get the Z transform of h of n. So we can also see that cos 2tn is multiplied with un. If I can find the Z transform of this particular thing, and then I can use this second property so that e to the power n I can consider this as a and a to the power n, then I can exploit this particular expression. So our main job will be for this question to find the Z transform of hn. First, we need to focus on the Z transform of cos 2t. And for that also, we need to carefully proceed because directly finding the cos 2t and z transform could be uh, difficult. So let me use some properties here also. So let's change the color of the pen. So let e to the power minus j 2n t. So I can write it as e to the power minus j 2t to the power n. Now let me take the z transform of e to the power minus j 2t in. I will take the z transform this thing. So a to the power n multiplied with nothing means we can consider there is multiplication of un. So I can use this form. So it would be z divided by z minus e to the power minus j 2t. Fine. Now I can use some more relations. I'm just multiplying in both numerator and denominator with the same factor e to the power minus j 2t, and here z e to the power minus j 2t followed by z e to the power j 2t. So if I just multiply this, so it will give me cos 2t, then it would be minus j sine 2t divided by. Now if I multiply these two things, so it would be z square minus z e to the power j2t minus z e to the power minus j2t. And then the multiplication of these two will effectively give you 1. So what I can do is that e to the power minus, so why this 1 is coming? So e to the power minus j2t multiplied with e to the power j2t. So I can consider this as z and this as z star. So z into z star is basically mod z square. And mod z is what? E to the power j2t mod square. So e to the power j theta, any form of e to the power j theta is 1. So it is basically 1 squared is equals to 1. So by that logic, this thing is coming over here. So z transform e to the power minus j2t to the power n is is giving you this sort of relation. So if I just copy this part again from here, so it would be like this. Now I can again just rewrite it as z minus cos 2t minus j z sine 2t divided by z squared. So here I can see that if I take z common minus z common out from these two relations, so I can write it as 2z cos 2t, as because e to the power I theta plus e to the power minus I theta divided by 2 is equals to cos theta. So by exploiting that rule, we can write it like this. And this is z transform e to the power minus j2t to the power n. So this has two parts. One is the real part and one is the imaginary part. So it would be z squared 2z cos 2t plus 1. And then if I just take plus and then jz sine 2t divided by z squared minus 2z cos 2t plus 1. So this part, let me see whether I can use some properties or not. So I can conversely, again, I'm writing it e to the power minus j 2nt. So this thing, I can write it as z transform cos of, sorry, here it is in n into t, cos of 2tn minus j sine 2tn or 2nt, whatever you, you want to like to write. So it would be cos 2t over here and then z square minus 2z cos 2t plus 1. And then it would be minus j sine 2t multiplied with z and then z square minus 2z cos 2t plus 1. So z transform, I can say that z transform of cos 2nt is basically z minus cos 2t divided by z square 2z cos 2t plus 1. Okay, so which I was telling this fact that if I can find the z transform cos 2tn, so then I can use this particular relation and then I can find the e to the power minus t to the power n multiplied with cos 2tn. So I can take, I can find out the z transform of that composite form. But before that, we need to find the z transform of this particular relation, that is cos 2tn. So that is what we have found over here, that the z transform of cos 2tn is basically reduced to this form. So if I just copy this part in the next page. So this is the z transform of cos 2tn. Now we are basically, we will be happy to find the next part. So the z transform e to the power minus, sorry, here it was e to the power minus t to the power n cos 2nt. So rule is that if a to the power n xn is given, then the corresponding z transform will be what? Z transform will be x of z by a. So in each place, so there is a parenthesis is there that has been missed. So in place of z, I will be writing z upon a. So everywhere I will be writing z divided by e to the power minus t, z divided by e to the power minus t, and then cos 2t divided by z e to the power minus t whole square minus 2 into z by e to the power minus t cos 2t plus 1. Now if I just simplify this whole thing, so it would be z e to the power minus 2t. So I can write z minus cos 2t multiplied with e to the power minus t. And over here, I can write it as set. I can just take z square minus 2z cos 2t e to the power minus t plus e to the power minus 2t divided by e to the power minus 2t. So e to the power minus 2t, e to the power minus 2t, it will cancel each other. And then followed by that, I can write that z square 1 minus cos 2t e to the power minus t z to the power minus 1 divided by, if I take z square out of it, so 1 minus 2 into z to the power minus 1. So it would be cos 2t e to the power minus t, and then it would be e to the power minus 2t z to the power minus 2. So z square will cancel with each other. So the z transform of e to the power minus t whole to the power n cos 2nt, it will effectively give you this particular relation 1 minus e to the power minus t cos 2t z to the power minus 1 divided by 1 minus 2 z inverse cos 2t, then e to the power minus t followed by plus e to the power minus 2t and z to the power minus 2. And additionally, we need to define the ROC also, as because Z transform is incomplete without specifying the ROC. So we have been already seeing that which of the relation that we have to exploit is that this thing. So mod Z is greater than mod A. So I can write it as mod Z is greater than mod A. So effectively it is greater than A is what, e to the power minus 2. So e to the power minus t, and e to the power minus t is basically a scalar. So anyway, I can write it as mod z is greater than is equal to e to the power minus t. So let me check what is the final answer for this particular question. So mod z is e to the greater than e power minus t. So these are nullified. Now the second option is what we have cos in the numerator and denominator cos terms. So it has sign. So option C is also nullified. So option D is the correct answer, which is matching with our answer, that is 1 minus e to the power minus t into cos 2t and then z to the power minus 1. So over here, the sample, the all the uh, functionalities are matching. So therefore option D is the correct answer for this particular question. Okay, so going to the next question. So h of z is given as 1 minus half z inverse divided by 1 minus 3 by 4 z to the power minus 1, 1 upon 8 z to the power minus 2. A new filter is generated having an impulse response which has h1n is equals to minus 1 to the power n hn. Then what would be the transfer function of this filter? So this is the original filter or given filter. We need to find that what would be the h1z. So what would be the h1z that we need to find out. So it would be, let us start by solving h1z is equals to h1n set to the power minus n, and n is equals to minus infinity to infinity. But it is again, it is given that this is a causal filter. So as because it's causal, we can start from n equals to 0 to infinity h1n set to the power minus n. So therefore it would be minus 1 to the power n hn z to the power minus n. So n is equals to 0 to infinity. So if I combine this minus n with this z, so it would be h of n z it would be minus z rather. So z to the power minus n. So minus n to the whole to the power n is equals to minus n whole to the power minus n, because effectively it will give you minus 1. So therefore I can write it as n equals to 0 to infinity, and that is h of z. And I can conversely write it as, this is in terms of, if I write in terms of hz, so it would be z transform of h only z transform of hn is basically hz is equals to h of n z to the power minus n, and n is running from 0 to infinite. Over here, what is happening is that we are transforming it in terms of minus n. So in place of z, it would be h of minus n. So h1 z is equals to h of minus z. So now if I try to find the h1z from this particular uh, transfer function, so it would be effectively h1z is equals to 1 minus, in place of z everywhere I have to write z to the minus z to the power minus 1, or conversely it would be in place of z everywhere I have to put minus z. So therefore it would be 1 plus half z inverse. Okay. So then 1 plus 3 by 4 z inverse. Over here, z to the power minus 2. That means even power is there. So even if I put minus z, so the outcome will be positive only. So it would be 1 upon 8 z to the power minus 2. So this is what is the transfer function look like for the newly generated filter. So the correct answer is all with positive sign. Okay, so option C is the correct answer. So it could be H1 over here. So they could have written H1 in here. Okay. So this is the last question for this week 7. So the last question, these like HAS, they have given uh, Laplace transform as 2 divided by s square 4s plus 3. I can reduce it to s plus 3 and s plus 1. So I can rationalize it as s plus 3 and b divided by s plus 1. So this is h of s over here. So I need to find what is the value of a and what is the value of b. So to find the value of a, I can write it as a is basically HAS multiplied with s plus 3, and we need to evaluate at that particular location where I'm getting the singularity of this particular transfer function. So for s plus 3, the singularity point is basically s equals to minus 3. So I will evaluate at s equals to minus 3. So therefore, a will be is equals to, if I just multiply s plus 3 over here, it will be 2 divided by s plus 1, evaluated at s equals to minus 3. So it will be minus 1. So that means it will be minus 1. So effectively, if I don't calculate for b also, I can just say that it would be 1 divided by s plus 1 minus 1 divided by s plus 3. So if I do the calculation for b also for you, so it would be HAS multiplied with s plus 1. And over here, the singularity point is at equals to minus 1. So it would be 1 divided by, oh, sorry, so it would be 2 divided by s plus 3. And as because s is minus 1, so it would be 1. So it would be 1 upon s plus 1 minus 1 upon s plus 3. Okay. So if I take the corresponding time domain signal by taking the inverse Laplace transform in both the right hand and left hand side, so I will get each AT is equals to e to the power minus t multiplied with ut minus e to the power minus 3t multiplied with ut. Or conversely, I can write it as e to the power minus t e to the power minus 3t, and then I can just combine the multiplication of u2 with this. Now they have given this particular relation that we have already seen in question 2. So Hn, the digital signal or the discrete signal, is equivalent to the sampling of the analog signal with a period of t. So I can write Hn is equals to HANT. So thereby I can just replace this e to the power minus small t by nt. So e to the power minus nt, and then e to the power minus 3nt, and then unt. And unt I can write it as un. So therefore e to the power minus nt minus e to the power minus 3nt multiplied with u of n. So over here we can uh, so this is what is the digital or the discrete signal looks like. Now what we have to do is that we need to take the uh, Z transform so that we can get H of Z, and H of Z is indeed it's a form of nd by nz by dz, and we need to find what is this nz or the numerator part. So let me just solve it. So h of n is equals to e to the power minus t, t into n, so it is nt, so t n, so e to the power minus 3nt, and then I can write it as h u of n. So I can even write it as e to the power minus t n un minus e to the power minus 3t, and then I just take n over here and then multiply it with un. So this is the signal, discrete domain signal. So if I take Z transform both the half, so for both the half, if I take Z transform, so it will give me H of Z, and then it will give me 1 divided by 1 minus e to the power minus t z to the power minus 1, and minus it would be 1 minus e to the power minus 3t z to the power minus 1. Now if I just combine these two, I will get 1 minus e to the power minus t z to the power minus 1, 1 minus e to the power minus 3t z to the power minus 1, and then it would be 1 minus e to the power minus 3t z to the power minus 1, followed by it would be minus 1, and then plus e to the power minus t z to the power minus 1. So nz or the numerator part will effectively reduce to e to the power minus t e to the power minus 3t, and these two are joined to multiply with z to the power minus 1. So this is what the nz will look like. So it is basically the option B, e to the power minus t minus e to the power minus 3t, and that is multiplication with z to the power minus 1. So over here, the final answer is option D. Okay, so we have solved the week 7 quiz. So now we'll head towards the recapitulation part for week 8. So in week 8, we have been already covered some FIR filter designing techniques by window method, and the main technique, and we have also talked about what is a bilinear transform. So a bilinear transform has this particular notion that we need to construct an FZ where in the analog prototype, wherever there is S, will be converting this, will be replacing that S by an FZ, and FZ indeed should be a rational function. And if FZ is a rational function, then the corresponding digital domain transfer function, it will also be a what you call, it will also be a, rational function. And additionally, if the poles of h of s are in the left hand side, So then it should be mapped in the units within unit circle so that it can ensure the stability. And if the poles in the Laplace domain, they are in the positive side, so in the digital domain filter, the filter will have the poles in the uh, part which are basically outside to the unit circle. So which basically lead you to an unstable filter. So with this, the bilinear transform was covered, and the main theme of this particular week is basically we know what is DFT. Now, still DFT has a huge computational complexity associated with that. That is bgo of n square. So computation of any multiplication is basically very resource hungry uh, operation. So for each and every mathematical operation or each and every uh, um, calculation for the calculating the CFT, we need to investigate some algorithms, efficient algorithms by which we can reduce the computational complexity. And by reduce the computational complexity, I mean basically reduce the computational complexity of multiplication. So if I am able to reduce the multiplication, so indeed I will be able to reduce the computational complexity. And that is what basically covered in this particular week by introducing the FFT algorithm. So, and most importantly, there are several forms of FFT algorithms are there. For example, decimation in frequency and other forms. But in this particular course, we will be mostly focusing on FFT using decimation in time. So we'll be using DIT FFT for implementing the DFT or the discrete Fourier transform. So let me take a sequence. So let us take xn is a sequence which has x0, x1, x2, x3, x4, x5, and x6. So I can, as because this is a decimation in time, we know what is called decimation. So roughly speaking, let us consider we'll be using some downsampling process, and I can take two polyphase decompositions. So one could be only the even parts, or the I can take even more samples. So I will be using radix too. So I have to take uh, samples which are in the order of 2 to the power r. That's because I'll be working on radix too. So x6 and x7. So it will give me 0 to 7. That means total 8. That means 2 to the power 3 for 4 and correspondingly x6. And followed by that, I can take another polyphase which will have only the odd parts. Okay. So Gn will comprise of x0, x2, x4, and x6, and Hn will comprise of x1, x3, x5, and x7. Okay. Now, given these particular sequence, if I first try to find the DFT of xn, so the DFT of xn, xk is basically xn e to the power minus j 2 pi n k divided by n. So over here n is basically 8, as because I'm working with 8-point sequence. So it is basically 0 to n minus 1, and I can break it down to two different summations. So one could be x of, so this is x of 2r, and this is x of, so this is x of 2r plus 1. So let me write it clearly. So this part is x of 2r, and this part is x of 2r plus 1. So x of 2r e to the power minus j 2 pi, then a 2r over here, then k, then n. And then I can write another component. And here, as because there are total 8 samples, so over here there are total 4 samples, 4 sample. That means n by 2 samples. So the summation will run from 0 to n by 2 minus 1. Over here also 0 to n by 2 minus 1. And then x of 2r plus 1 e to the power minus j 2 pi 2r plus 1, then k, then and here, as because I'm doing an n by 2 point of DFT, so I will just write it later. So it would be x of 2r e to the power minus j 2 pi r k n by 2, and then x of 2r plus 1 e to the power minus j 2 pi. And over here also I can just take 2r plus 1 k n upon 2, and then n equals to 0 to n minus 1, n equals to 0 to n minus n by 2 minus 1. Sorry. So over here, what I'm doing is that I'm taking n by 2 point DFT over here. So this is basically the DFT of this thing. So I can write. Sorry, I guess there is some issue with this pen. So this is what is g of k, and I can take one of these twiddle factors out of this thing. So I can even write it as like it is some, yes. Got the destruction. Actually, I think software, there is some problem with the software. Okay, I guess it's fine now. So it would be 2 pi, then 2r, then k by n, and I can take one of the factor out. So that would be to the power minus j 2 pi k by n. What here? So I can write it as e to the power minus j 2 pi n multiplied with k, and this is what, if I take this 2 in the denominator, so it would be by 2, and again what I'm doing over here, I'm doing the n by 2 point DFT over here also. So this is basically h of k. So xk, I can write it in this particular way. And there is a very common term that is, we call it as a twiddle factor. So twiddle factor is nothing but e to the power minus j 2 pi by n. We write it as wn. And as because over here we have a factor of to the power k, so I can write it as e to the power minus j 2 pi. Sorry, j 2 pi k by n. I can write it as w k. So the twiddle factor, I can write it as wk to the power wk, and which has a suffix of n. So if I exploit this structure, apparently you may think that the computational complexity is still the same, that is n square. But what we have got out after doing this particular breaking and all. So the thing is that we can get some other features from this n by 2 point DFTs. As because it's an n by 2 point DFT, we know that DFT is a periodic DFT has a periodic property. So X, so from this, if I take Z0, it will be equal to G4, as because this is a endpoint DFT, like this is an endpoint n by 2 point DFT, and effectively it's a 4 point DFT. So G0 will be is equals to G4, so that I don't have to compute this G4 again. I can just use G0. So using this particular property, and over here in this particular H also, so H0 is equals to H4, and likewise H1 is equals to H5. So I can just use the upper half or any of the halves of G to calculate, to basically get calculated to this G4 and H4. If I have H0, I can concurrently use it as H4. So this will reduce the computational complexity, and we'll see that how much reduction is there. So for that, let me just try to exploit the butterfly structure to get the DFT representations. So initially it was an endpoint DFT. Now these are, so initially it was endpoint, but these are individually n by 2 point DFT. So this is n by 2. So I can write it as G0, G1, G2, and G3. And over here, I can write H0, H1, H2, sorry, it is H2, and H3. And whatever the DFT is like X1, X2, X3, X4, X5, X6, and X7. So this could be a little bit clumsy. So if I find X0, it is what? G0 plus W N0 H of 0. So G0, then W0 is multiplied with W0. Sorry, this is WN0. WN0. So this is how I'm getting X0. So likewise, and if I write X of 4, it would be G4, then WN4, H4. So already I have told that H4 is H0 and H4 is H0. So now what is basically W4N? So W4N is basically G0 minus 1 multiplied with WN0 H0. So over here it will be a minus 1. And over here there is a summation. Wherever 2 points meet, I'm using it as summation. And whenever there is a multiplication factor is associated with this, so there will be a this you can think of a game or a multiplication factor. So by this logic, if I can construct x1 by exploiting these two things, so it will be like this, and this will the butterfly like this, and this will have the Whittle factor Wn1, and over here again this will have -1, this will have -1, and consequently the butterflies will be, sorry, so I need to extrude this one. So over here the butterfly will be like this, and here it will again have the same structure. Here it will put W2, here it will put W3, -1, and then would be the last output. So in this way, we are getting the DFT outputs. Now, if I think that I have got these representations, so G0 is what? G0 is basically X0. If I just consider the sample domain representation. So these are the even things. So 0, 2, 4, and then followed by 6. You know what, here it is 1, 3, 5, and 7. So here I am getting 0, 1, 2 in an order. However, the order is messed up over here. So this order we can get this particular order using a bit reversal technique. So bit reversal technique. So given this order, this order is fine. So 0, 1, 2, 3, 4 up to 7. These are has been ordered correctly. However, here the order is messed up. For example, x0, x2. So how I'll be able to comment about that after x0, what sample will come? So here this is a 8-point DFT case. So I can just consider, okay, the upper half will be the odd parts and lower half will be the upper half will be the even parts and lower half will be the odd parts. But what about the if I have been given a 32-point DFT, a 64-point DFT, then if I just randomly ask to just tell me what would be the sample value at 21st position. So then I'll be able to just answer that particular question. So we can comment about that question by using a bit reversal technique. So bit reversal technique is if your radix is 2 to the power r. So for example, in this case, we have a 2 to the power 3 as because we have 8-point DFT case. So I can represent this 8 points using 3 bits. That means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this gives me 0 to 7. So this gives me from the 3-bit representation. So over here, if I just make the reverse of this bit, so it will be same as 0, 0, 0. It will be 1, 0, 0. So this was 0, 1, 2, 3, 4, 5, 6, and 7. So the positions, let us check how the positions are basically giving you this particular value. So if I just take the inverse over here, so it would be 0, 1, 0, then 1, 1, 0, then 0, 0, 1, then it would give me 1, 0, 1, then it would give me 0, 1, 1, this will give me 1. So this is effectively the 0, then 1 0 0 is the fourth one, then this is the second one. So in this fashion, we can just exploit that how we can get the these systems, these representations. And additionally, we can so this has been given an n by 2 point DFT. We have break the DFT in an n by 2 point fashion. So given this n by 2 point DFT fashions, what we can do is that we can think of n by 4 point DFTs to get these DFT representations. And we'll stop till we get the uh, n by 8 point DFTs. So it would give me 2 of this over here. And we'll have the similar butterfly structures over here. And over here also. So this part is your n by 4 point and this part is your n by 8 point. So in this way, we can actually go from this from the right to left, and we can create the butterfly structure, overall butterfly structure. And we have represented the 8-point DFT using 3-bit representation. So over here also, how many stages are there? This is the stage 1, stage 2, and this stage 3. So if you have R point DFT, so for example, if you have N point DFT, then you'll be having, and this N is equals to 2 to the power R, then you'll be having R stages of cascade of the butterfly structure. Okay. So with this, there have been a great discussion done by Professor Chakravarti. However, as because it is not within my scope that I will be discussing each and every point but precisely. So my main concern is to solve the problems related to this particular week. So let me just move to the questions for the practice questions for this week 8. So in week 8, the first sample question is this one. So we have been given a sequence x of n, which is having 0, 1, 2, 3. That means this is a 4-point signal. So effectively, this will be 4-point DFT. And we need to find the DIT FFT of this thing. So for that, we need to draw the diagram. So I can start drawing the DFT diagram. So x0, x1, x2, and x3. So when I'm doing this x0, x1 computation, so the butterfly will be, so if I just look at in terms of the previous architecture, so this could be G0, this could be G1. So your G is basically 0, 2, and your H is basically 1, 3. So this would be H0, this would be H1. So X0 is H0, then H0, and there will be a quiddle factor. So that quiddle factor will be W 4 0 over here. So here also we had seen that the quiddle factor was WN0. So by that logic, it will be W40, obviously. And here there will be a summation. And if we just redraw the second structure of the butterfly, so here it will be -1, followed by that here it would be it will take W4 1, and again it will have this structure over here. And Z0 is what? Z0 is basically X0 and X2, and over here it is X1 and X3. So it is X0 is equals to 0, X2 equals to 2, X1 equals to 1, and X3 equals to 3. So here we have done 2.80, 2.80 each, but we will stop at the over here. So here the butterflies are just this one. So it is over here. So over here it was W 0, and as because here what we are doing is that we are taking W40 over here, it would be halved, so it would be W20, and again W20 is equals to W40. So by that logic, I can say that it could be W40. So I can write it as W40, and over here also I can write W40. So I need to find what is W40 and what is W41, and then I can just proceed with this multiplication and addition, and then over here it will be again -1, over here it will be -1, and the rows are like this. So here we need to find what is W40. So W40 is basically e to the power minus j 2 pi 0 upon 4. So 1. W41 e to the power minus j 2 pi 1, then 4. That means e to the power minus j pi upon 2. So cos pi by 2 is 0 multiplied by minus j. So W41 is equals to minus j. So now let me do the multiplications. So over here 0 was coming. Now you have multiplied 1, and then 0 is added with 2. So the output over here is 2. So likewise, this is 0, this is 1, this is 0, this is -1 multiplied with 2. So it is -2 over here. Fine. So over here also the 1 is coming, and over here it is 3. So 1 plus 3 is equals to 4. So 1 minus 3. So it is -2. Fine. Then for this next stage, so over here 2 is coming, and from this point 4 is coming. So 2 plus 4. So here 2 is coming, and from here 4 is coming. So 2 plus 4 is equals to 6. Then for this x1, so at this particular position, -2 is coming from this side. So -2 is coming from this side, and followed by that -2 multiplied with this thing. So this thing is nothing but -3. So it would be plus 2j. Followed by that over here for x2. So here 4 is coming, then 4 is multiplied with 1, and over here 2 is coming, so 4, then it is -4 plus 2. So this is -2. And lastly, this structure will be at x3, it would be nothing but it is -2 coming over here, so -2, and over here it is, if I take -2, then -1, then W for 1, so it would be -2. So -2, -2, -2, -1 will be +2, and this is -3. So this will be -2. So your DFT using this particular DIT-A50 method. So your output will be 6 -2, 2j, -2, and -2, -2j. And obviously it will have the complex representation as because you are doing DFT, it has a complex exponent basis function, it will be -j theta. So obviously it will be -j theta will give you the rectangular form of some representation like -2 plus 2 so and -2 -2 so. Okay. After that, over here, a question is basically given like a sequence xn of length 32. That means n is 32. So n is 32, I can write as 2 to the power 5. That means we need to represent the bits using 5-bit representation. Okay. So after that, what we have to do is we need to compute a 32-point DFT using A50 decimation in time algorithm. In the revised order data vector at the A50 input. So we need to revise the order of the A50 input. That's because we have seen that in the output, the order is okay. That is 0 to 7. That is written accordingly. But in the input side, the order of the data is basically messed up. So we need to find the correct order of the data for any particular given endpoint DFT. As because if your endpoint n is sufficiently less for that particular moment, okay, you can tell that at which position which of the sample will come, input sample will come. Now, when your endpoint DFT, if it is like let's say 64-point DFT, 124-point DFT, 2048-point DFT, then it is very difficult for you. So to comment about the position of the input samples at a certain interval time. So therefore, you need to have some methodological representation. So that is basically given using the bit reversal technique. So we need to talk about the position x21 will be at what position? X21 kahan rahega? So we need to find that what would be the actual position of the of that particular sample. So we need to find 21, which is obviously it is in the decimal domain. So we need to find the equivalent binary representation. So to find the equivalent binary representation, we know what we have to do is that 21 divided by 2, and then it is 10, then it is 1, 5, so 0, 4, so 1 into so this would be 2, then this is so this is 1 over here and with the quotient with 0. So I can conversely say that 21 in decimal is equivalent to 1 0 1 0 1 in the binary domain. Now if I just take bit reversal. So if I take bit reversal, I can see that this is a symmetric representation. So even if I just uh, reverse it, so I will get the same thing. So 10101 into. So effectively, this will give me again the same position. At 21st position, I will get x21. So which is 21. Okay. So another question, we have been given that this is the DFT part, this is the DFT section, and this is the input sample section. This is the sample section. And we have been given this particular structure where the multiplication and addition connections are already been defined. And we need to find the x of 1 such that the W6 is basically exponent of e to the power minus j2 pi by 6. And given that x1, after finding that x1, we need to find the coefficient a1, a2, a3. What would be the coefficients? And in the next page, I have given the uh, uh, options. So we need to find what is the value of A1, A2, and A3 such that the uh, X1 will be in the perfect order. So this is a 6-point DFT as because we have samples from 0 to 5. So let us just start exploring the signal flow graph to get X of 1. So X of 1 could be whatever coming over here that is multiplied with A1. So A1 multiplied with X0 is coming from this side, X0, and then from this side, X3 into minus 1. So I can write it as minus 3. And then obviously it is multiplied with A1. Okay. Over here, again, A2 will be multiplied with X1 minus X4, followed by that over here it is basically A3 multiplication, and this is X2 minus X5. X2, sorry, this is X2 minus X5. Now we know that Xk is basically summation X of n W n A n. So that's because W is e to the power minus j 2 pi by 6. So we need Kn and multiply by 4. Now if I write X of 1 and n is equals to 0 to n minus 1. So it would be X0 multiplied with this Kn over here. So it would be W and n is 6. So W6 0. Then followed by X1 W6. So it would be so it would be 1 multiplied with 1. Let me just write X1 is equals to Xn W n n n equals to 0 to over here it will be 5 only. And I can even further rewrite it as 6. So it would be now X2 W6 and over here n into 2, then X of 3 W6 over here n will be 3 x4 W6 4 x5 W6 5. Okay, so from here I can see that this is x naught and W60 is basically 1. Fine. Now let me check what is the value of W36. W36 can be written as e to the power minus j 2 pi k, that is 3 divided by 6. So it will give me 2 over here, and then this is e to the power minus j pi, and e to the power minus j pi is nothing but minus 1. So I can write it as x naught minus x3 multiplied with 1. So by that logic, A1, oh sorry, so A1 is 1. So first answer we have found it. So option 4 are nullified. Now we need to find uh, x1 minus x4. So for x1 minus x4, if I just exploit this relation, so this is W6 1, and for x4 it is written that x4 W6 4. So we have a relation that we can exploit, that is applicable for this Quidel factor. So Wn r plus n upon 2 is equals to Wr multiplied with Wrn effectively. So Wn n upon 2. So just now we have seen that n is 6 and n upon 2 is 3. So the output is what? Minus 1. So this could be minus Wr n. So Wn r plus n upon 2 will have this sort of relation. So over here we can see that W6 plus 3, that is n upon 2. So W61, if I consider it as one particular sort, and then 1 plus W1 1 plus 3, this will basically minus of W16. So now I just need to find what is W16. Otherwise, let me just check. So W x of 1 minus x of 4, and these two are same as, that means W46 is equals to minus of W61. So this will be W61. So this is what A2 looks like. So A2 is W61. So given this, A1 is this one, W16. So let me just stop solving for this A3. So I can just conversely say that option 3 is correct one, as because A2 cannot be W2 to the power 6. If I just solve the last part also, that will not take much time. I can write it like this for W. Let me just check which of the conditions are next. So W2, W5. So X2, W2 upon 6 and X5, W6 then 5. So W26 is basically minus, sorry, W56 is basically minus of W26. as because you can just exploit this particular relation. If you put r is equals to 2 and n by 2 is equals to 3, so that means 2 plus 3 is equals to 5. So W56 is basically minus W of 2, 6. So this will give you x2 minus x5, and the Quidel factor corresponding to this operation will be W62. So the last answer will be W62 over here. So option 3 is the correct answer for this particular question. So moving to the next question. So in the next question, we have been given xn, which has 8-point sequence, and therefore the DFT is also an 8-point DFT, and the DFT is written as x of k. Then the sequence yn, whose DFT is of this sort, is given as. We need to find what is the sample response of yn, which has a DFT of this sort. So let us consider yk is given as n upon 2, 3k, and xk. So this thing I can write it as e to the power minus j 2 pi 3k divided by n upon 2 and then followed by xk. So e to the power minus j 2 pi k 6 by n xk. This is what is yk looks like. Now we know that if I multiply any complex exponent with a DFT, I will not get a linear shift. I will get a circular shift. So that what sort of circular shift I will get, that I need to just revisit. So I will show some of the samples and then you can just infer with the natural consequence that how can I get the original sequence time. So x, I guess. So over here, if we have been given an xk, so for that I can compute what is called xn by using this particular relation, that is 1 upon n, and k is running from 0 to n minus 1, then x of k e to the power j 2 pi nk divided by n. So over here we have been given two sorts of equations. One is that output yk is related with some complex exponent multiplied with the original DFT. So over here that yn will be nothing but 1 upon n yk e to the power j 2 pi nk by n. Now I can write yk conversely as this thing. So 1 upon n summation xk e to the power minus j 2 pi k 6 by n e to the power j 2 pi nk divided by capital. So if I just exploit this at this particular position, so it would be 1 upon n summation xk, then e to the power minus j 2 pi by n, that is fixed, and k is also fixed. So therefore, we have been left with n minus, or we can take plus over here. So n minus 6. So when I will open this bracket, I will get the same situation. Okay, and the summation variable k is running from 0 to n minus 1 over here. So that is what yn looks like, and this is what xn looks like. Now I can say that If I take y of 0, then what is the situation that I'm getting over here? So this is 1 upon n. This is what is x0 and e to the power minus j 2 pi k 6 by n. And over here, if I just take the same operation, so I will. So let me just go to the next page and let's just copy some of the required formulations. Otherwise, here it would be too comprehensive. So this is the first relations that we are exploiting over here. And this is the second relation. So I will do the inference in this next page. Let us take y of, so this is n minus, so this is n minus 6. So over here it will be n minus 6. Okay, so if I take, let's say y7, so here it is j 2 pi n k over here. So this is 1 upon n and it would be xk e to the power j 2 pi k, and this have been multiplied with n minus 6 over here. So I can just write 7 at this particular location, and then followed by that I can take n. And over here, what I can do is that I can take x of, let's say, 1 upon n summation x of k, and then e to the power j 2 pi k 1 divided by n. And then if I take x 1, then I will get 1 upon n, then x of k e to the power j 2 pi k divided by n. So in this fashion, I can say that y7 is equals to y1, and this way you can get all the samples. So you just have to put n equals to some value, let's say n equals to 6 in this particular equation, and then you will get some representation over here, and you need to compare by putting the uh, suitable value of n over here so that you can get the corresponding representations. So by this logic, you can get the whole sample, and let me just give you some brief idea. So you will get the sequence like this particular sort. So this could be minus 4, 5. And let's say at the first location, it will be n minus 2. So n minus 2 will be, you have total 8 number of sequences, and then you can just do an n minus 2, and then you will get this location. So 0, 1, 2, 3, 4. So that means over here, uh, you will get the following samples like 0, and then you can just put the values over here, suitable values. For example, y7, we have got x of 1. So likewise, if you put n equals to, let's say, 6, so for n equals to 6, you will get x equals to 0. So in this fashion, you will get the other values. So this is just a circular shift, circular right shift. So as because we are shifting the signal, we are shifting the components in the right hand side. So if let's say this is the input, so I will be shifting the samples in this particular order, and whatever sample I have been left over here, I will be shifting it like this. So this is the circular right shift. Okay. So moving to the next question. So next question, we have been given a big DFT structure. So in this DFT structure, the first question is what is the gain along the path emphasized in the figure? So this is the path which have been emphasized over here. So in this path, what is the gain? So first gain component is Wn 0. Then second component is -1. Then third component is W2n, and there are no components. So total gain will be multiplied with each other. So Wn0 multiplied with -1 multiplied with Wn2. Okay. So effectively, this is an 8-point sequence. So I can write it as W80 into -1 into W82. So W80 is nothing but 1. So 1 into 1 is -1. And then W28. So I can just calculate what is W28 e to the power minus j 2 pi multiplied with 2 and then 8. So this is 2. So that means it will minus j pi by 2. So I can just write it as cos pi by 2 minus j sine pi by 2. So cos pi by 2 is basically 0, and then it will give you minus j. So therefore it will be -1 into minus j. So it will be plus j. So this is actually what the gain looks like. And the second question is we need to compute what is x of 2. So computation of x2 will basically require the whole representation, like x2 is coming from these two joints. So this is first joint, this is second joint. Now these joint have this particular node. This node is coming from these two areas. So from these two areas where this area is coming. So this is the subsequent flow. Then at this particular location, the data is coming from these two places. So I need to see that I need to track first. I need to track which are the possible pathways from I can get x2. So I need to track each and every pathway. So I have to start for, if I start for this particular line. So first operation is basically coming from this area. Now at this particular location, the lines are coming from these two particular signals. Okay. Then over here, the signal is coming from these two areas. And lastly, we have reached the exact final stage. So this is the pathway. Now, the second pathway is this one. Now, along with that, you can see that some of the data is coming from this path also. So this is very tedious job. So this is the next line. And I guess I have covered each and every point for this particular line. Now, for this particular line, the data is traversing through this path, followed by this one. Now the data is coming from this area. So I need to track back this path. After that, I can see the data is coming from this area, followed by these two representations. And I can see that the last stage is this one. So for this, it is okay. Now again, the data is coming from this particular direction. Then there is again multiplied over here. Now at this point. So at this point, the data is coming from X3, and over here, the data is coming from this side. So this is what the full signal flow diagrams that we need to consider, and then you can just do it by yourself also. For example, it would be x0, then x0 is coming from here, so x0 plus x4, so here it is x0 plus x4, then x0 plus x4 is again going as it is, then over here it is uh, x2 is coming at this position, x6 is coming at this position. So x2 plus x6 multiplied with w naught n. So w naught n is 1. So over here, there is a multiplication of -1. So that means x0 plus x4 minus x2, x2 minus x6. Okay. So this is what this first part looks like. Now we have to wait for the second part. So x1 is coming as it is, x5 is coming as it is. So over here it is x1 plus x5. Then it is again coming as it is over here at this particular position. Now x3 is coming over here and x7 is coming in through this particular path, which basically added up over here, then multiplied with 1. That means x3 plus x5 at this particular location. This is x3 plus x5. Now this is multiplied with -1. That means this whole thing is multiplied with -1. Now x1, so sorry, it is x7. I have wrote x5. So at this location, x1 plus x5, and then this is the negated part, and which have been multiplied with w2n. So over here, the representation could be x of 1, sorry, it would be small x of 1 plus x of 5 minus x3 minus x7 multiplied with wn2. And then I can add this part and this whole part to get x2, so that you can do quite neatly. So as because it will be very difficult to draw the same structure in the next page, so I have tried to replicate the final answer over uh, this page only. Otherwise, this would be very difficult for me to replicate this whole structure in the next page. So this is how you need to just look back into all the positions from where the data is coming. So you need to track back all the points from where the signal flows are coming from, and then you can multiply with the corresponding gain, and then you just need to add it up, as because these points basically relate to the adder points. These are the adder points. So by this method, you can get what is there in x2 also. So just make this. Okay. So with this, I have covered this week 7 quiz, as well as a quick recap of week 8. I have covered the uh, DIT DFT part, and followed by that I have taken some of the questions which basically deals with the bit reversal technique, then finding the DFT using DIT DFT method, and some of the questions were also related with the properties of DFT, such as circle shift and all. So if you have any queries, so you can just unmute yourself and ask. I'll be happy to answer the questions. So probably this is the last class for this particular course, as because this is an 8-week course. The course basically ends on 15th of September, that means today. And this is the eighth live session. So therefore, uh, as because I solved the week quizzes after you get evaluated for that particular week. So by that logic, I have covered till week 7 quiz. So I was planning to take one more class so that I can cover the week 8 quiz solution also. I have mailed to NPTEL, but I have not got any reply from them yet. So if they allow me, I will take a half an hour class if it is possible, if they allow me. So I will take a half an hour class, as because I have seen that in week 8 the questions are pretty easy. They have taken some miscellaneous questions, like some of the questions are from circular convolution, some of them comprises of properties of DFT. One or two questions are there from FFT. So uh, it will take hardly 30 to 40 minutes to solve that particular quiz. So I will be happy to take that particular solution of the solution. Otherwise, if they do not permit to take class, what I will do is that I will upload the detailed solution in the presentation link. So in the course website, let me just show you that how to get to the course presentation links. So you just go to the course website, log in yourself. I have already logged in. So go to the course. There you will find that problem solving session. You just click it over here and then click on the problems. I can just enlarge it. Okay. So the problem solving session recording, you just click it over here. So one Google Sheet will come. So this link will take you to a Google Sheet. So in the Google Sheet, you will see there are two TAs. One is me and one is Bonimitra Kundu. So in my folder, you will see there are two links. So one link corresponds to the YouTube link and another link is basically the presentation folder link. So in the presentation folder link, if you just click it over here, I have given week 1 to week 8. So I have given both the unannotated uh, slides and the annotated slides. So you can use both of the slides so that